Hello everyone, I'm back in MECO Rocket Simulator. It's been a bit, so I've probably forgotten some things. There's still early access software, so keep that in mind. And I do have some suggestions in mind, but we'll get to that. I believe we're past the tutorials technically. It says missions now, and we are going to be broaching the subject of cooling here. The mission brief says, the thermal side of propulsion. Today we are building a cooled throat slice modeled on the RS-25, that's the Space Shuttle main engine, or the engines on the Space Launch System SLS. Hot gas on one face, liquid hydrogen on the other, a solid metal wall conducting heat between them. Well, I mean, there's also the outer wall, and well, anyway, we'll go with the model as it has right now. New components, solid. It models conjugate heat transfer, gas side convection, wall conduction, coolant side convection, all coupled in one place. I'm not entirely. We certainly had solid things before, like the chamber, so I'm not entirely sure why it's a new component solid, but I suppose we'll see. You'll build a hot gas throat and parallel coolant channels. That sounds right. Add a solid wall to couple them thermally. That sounds confusing. I mean, obviously there's a solid wall, right? But how do you even have a hot gas throat and coolant channels, right? You've got a throat, you've got coolant channels. What's this adding a wall thing? You know, you should have coolant channels through the. But I mean, I guess they're slapping the coolant channels onto the hot gas throat and then adding a solid wall inside. Okay. Chart key variables and capture a baseline crisis run. Oh no. Tune wall thickness and coolant pressure to keep the wall below 800 Kelvin. Two boundary types in play. Hot gas inlet is a node gas inlet and coolant inlet is a node inlet. So, okay. Well, we have to create a new model. All right, build the hot gas throat. Well, let's go to that. Add node gas inlet. And we name this. Okay, so actually this is the first thing that I would like to propose as a suggestion if it's possible with this setup. Normally when you have these nodes, some of the variables are changeable here instead of in a separate menu on the side. I don't think it's the best thing to constantly have to open this menu on the side when you could just click on this and rename it, for instance, or have some of the variables listed here. To give an example of this, I will offer Blender as an example. Okay, so Blender has this node structure. In fact, the node structure of MECO Rocket Simulator reminded me of Blender's node structure. There's for shaders, and you can zoom out and you can have quite an array of nodes, and a lot of people who are into nodes in Blender can build entire things just with the nodes. But one thing you'll note about the nodes in Blender is that they have their variables right here. So you can scroll around. You don't press a plus button in order to add them. You can just add them with a right click, and then you have your list of various nodes like so. But you can change things right here, and you can type variables in right there. So if you wanted to rename something, you could just do so directly without accessing a separate menu. So if we wanted to rename this, for instance, or change other variables, we can do that directly in the node area. And that is a lot handier because you can see how what the numbers are all over the place instead of changing what you're focused on. So that's just, if it's possible to implement that, that is my suggestion. So right here, I mean, yeah, you can have all the connections. Blender has all these connections too, but it'd be nice in this hot gas inlet if we just had the information right here instead of having to. I mean, is there really much? It just says these gases. And we want to change that to oxygen, hydrogen combustion. But we could have just changed that here. So on a drop down, just like in Blender. So that would be nicer. if that could be managed. Anyway, add branch gas named hot gas throat. Oh, and then whenever I press enter, it actually hides that. I don't need that. If you could have some other way of hiding it except for enter, that would be wonderful, because I keep accidentally hiding it like that. Okay, so circle, radius 13, number of channels 1. Okay, and then passage roughness. Well, yeah, we don't have a passage roughness here. What's this? Branch gas. Okay, well. Okay, so we want now a node outlet. And presumably we can do this. Hot gas outlet, we connected all that stuff. Set the boundary conditions with the control parameters. Set the parameter type to pressure. And we want 207 bar. Connect that to the pressure thing there. And another control parameter. This is this time oxidizer fuel ratio. They want 6.032. Sounds okay to me. And that's over here. And the outlet is just to atmospheric pressure. Oh, because we connected it, we don't actually have to set the parameter type, so maybe just connect it first and have it set the parameter type. So the RS-25 chamber has a 207 bar chamber, and that ratio. Okay. Now we have to build the coolant channels. Now, how do we do this? 390 narrow rectangular channels running parallel to the hot gas, right? Yep. Pick a node inlet, not a node gas inlet. Okay, and we are going to name this coolant inlet. Set the liquid, again with the enter closing things. Liquid hydrogen. Add a branch. Coolant throat channels. I pressed enter again. So we sort of have this parallel thing going, which is interesting. And we have to have more control parameters. There's that solid. There's a solid there. Well, I'm going to connect that first. And yes, it sets pressure. Oh, the inlet one is 307. Well, at least I can copy and paste. Okay, we have built the coolant channels like this. The solid is what couples the hot gas and coolant thermally. It models heat flow from gas through wall to coolant using finite difference one-dimensional conduction, with boundary heat transfer correlations doing the convection on each face. Okay, fine. Let me just add the solid then. Guess we'll be here. Fine, let me get some room. I'm gonna assume that we need to plop it here. The L though is gonna sort of have to reach around that ways though. And the material is, I guess that's some sort of nickel alloy. Thickness subdivisions, We have to put the number of channels in here as well. It couldn't pick that up. Critical radius. See, now they should explain what these numbers do. Are what Bart's needs to compute gas side heat transfer, but that doesn't tell us what they do. Tune thickness later. Thinner walls cool faster, they're also structurally weaker. Pick your trade. Well, easier said than done. Get the right variables on the chart before we do anything else. Okay, we are charting the right stuff. Max time, it wants 0.05 seconds, not 10.05. Run. Well, there's the baseline apparently. The hot gas in the throat is 3653 Kelvin, and the wall temperature is climbing here. With the geometry and pressure you just set, throat wall should be greater than 800 Kelvin. That's the whole point of the cooling crisis. If it isn't, you've already tuned something. You've already done something good. Revert the thickness back to 1.5 millimeters. 1.5 millimeters is not enough. We can see that it's past the 800 Kelvin. Now, tune the design until cooling actually holds. Knobs you can turn. I wish there were knobs. Wall thickness on the throat wall, coolant inlet pressure. Well, we had pretty high pressure. 390 sounded like the right number of coolant channels, so let's just make the wall thicker. Say 2 millimeters. No, that didn't do anything. Okay, maybe not. Well, it said the target is wall thickness 0.7 millimeters. What happens if we do 0.7 here? Oh, okay. Well, I mean, it strengthens it, but we want it to get cooler, so... Alright. Well, then maybe we can have less. Does it model the fact that the wall is too weak? I mean, what if I just make it 0.1? Oh, well, that sort of failed. I guess that means it exploded. Still presumably exploding. Oh, there it is. Gets nice like that. Okay, well, we can have it all the way down to 0.3 millimeters. Coolant mass flow, it actually wants within 10% of 13 kilograms per second. We're only at 1.2. So we mainly just need a whole lot more coolant. And that means increasing the size. The truth is, these variables aren't independent, right? The thickness of the wall can potentially limit, I mean, especially since you have a certain number of channels, can potentially limit how big they can get. Because the throat's only a certain size. But we'll ignore that for now, I guess. Okay, that's 16.2, that's more, but then there's no chart here. Okay, now there's a chart, but it's too hot. It actually increased in temperature with more width. It's going to 965, basically. So about 300 channels. Well, that definitely increases it, but not by much. Number of channels, width or height on coolant channels, inlet pressure, fine. Let's change the pressure. That's one way to make sure you've got more flowing through, aside from changing the size of the channels. Well, I've changed everything. Maybe I need to change the coolant pressure a whole lot more. 600. Thing. Well, increasing the coolant pressure did not help anything. But it does want coolant mass flow to be increased. Well, it said wall thickness greater than 0.7 millimeters, not less than. Fine. 0.8 then? Well, then it goes like that. That doesn't help anything. Does it have to be greater than? Thinner walls move heat faster but break first. Real engine keep walls as thick as possible for durability. Well, I'll keep it minimal. Once greater than 0.7, let's say, whoops, 0.71. Just to meet that requirement. Small pressure changes move flow a lot. Great. Well, do we want a pressure drop then? Oh, the pressure drop is the main thing. I'm wondering how this actually works then, though. I'm also wondering what the significance of this number here is. But okay, well, there we've got a very low temperature, but we've got a huge amount of mass flow there. Okay, now we've got that below 800 Kelvin, but our mass flow is too high. So maybe reducing the channel size. Okay, now it's too low. Oh, now we've got close enough. So there we have it. Basically, it's because we needed to have 307 bar up there, 275 bar there, and so a reduction in pressure along it. I mean, it's possible if I guess it's because of the temperature change, the pressure wouldn't drop then, so because the pressure goes up as the temperature goes up. So anyway, a little bit complicated, and it's not explaining it super well is the problem. And at 0.14 and 0.28 there, just above their thickness requirement. Okay, complete mission. Build a cooled throat slice modeled on the RS-25 regenerative cooling. If you say so. I guess they're happy with below 800 Kelvin. Well, I didn't get it to 207. So I guess they want the outlet for the coolant to be the chamber pressure. I didn't get it all the way down like that. Oh, I clicked out like that. That didn't work. Okay, 6 missions of flow and pressure. From here on out, we're thinking in torque and RPM. This seems like something different. So we've done cooling as far as it's concerned. And I have some questions about that cooling, but I don't think it's going to answer them for me. We will be going on to the turbines, a fast fake turbine driving a slower fake pump. How fake is the question, but we'll have to find that out next time because I think this is going to take at least half an hour. And I don't know how much video time that translates to, but anyway, it seems like cooling is definitely its own topic and deserves its own video. So there you have it, how MECO Rocket Sim does cooling. And with that, I'll say thank you for watching. I hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below. And I'll see you next time.